So we've done our car lab, and in this car lab we collected the time and position data. Now you may have only done 2 trials for your position data because after the 3rd trial the car's battery may have started to die. That's why we probably only recorded 2. But either way, we can get the average by taking your first plus your second trial plus your third trial and divide it by your number of trials. In that case would be 3, and that's how you're able to get to your average. And in this case here we have this position, and then the units for position are meters. We also recorded the position at certain time intervals, and the time has units of seconds. So we usually just denote that as an M and an S. And we recorded the time going from 0 to 2 to 4 all the way up to 20 seconds, and we recorded the positions accordingly. Now what we were asked to do is trying to find the relationship between position and time when velocity is constant. And so there's some ways we have to show that this velocity is constant. Now as we recorded some data, what we did is we had to put down this piece of tape. Put down a piece of tape. And as we put it down, we put the piece of tape down wherever the car was after 2 seconds. And so it should have looked something like this, where the tape is evenly spaced out. The tape should be evenly spaced out because we measured where the car was. We measured it by recording the time and the position data. So at this point in time, where we put that first piece of tape, that's 0 seconds and 0 meters. And so this is that initial position. So that's where we're going to use this x sub 0, because that's initially where it started. That time 0, it's at 0 meters, and this is the position where it started. And then we come out to here where at time equal to 2 seconds, and then time equal to 4 seconds, and then time equal to 6, and so forth. Every 2 seconds, we were able to record the position and the time data. And so we can get to a displacement here by getting from where it started to where it ended. And then this whole distance would be this displacement from where it starts to where it ends. If we are concerned with the displacement after 6 seconds, we can get to this delta x, which is the displacement, in terms of meters. So what this displacement means is, it's kind of a way of saying is how far from where it started. And it could be whatever we're talking about. It could be this car, it could be something like a racer, anyone that's moving. We are going to have a displacement because you're going to move to a different position and you're going to be going a certain distance. So you're going to get to a displacement. And we can calculate a displacement. Let's say at 6 seconds, its position was 1.95 meters, and at 2 seconds, let's say its position was 0.65 meters. Now we can get a displacement, a delta x, after 6 seconds. And so we can get a displacement after 6 seconds by getting its final position minus the initial position. And so the final that's where I would count at 6 seconds. If we're trying to find the displacement after 6 seconds, it would be, in this case, the 1.95 meters. I'm just taking a data point from here, 1.95, and I'm going to subtract out the initial position of 0 minus 0 meters. So I would have a displacement of 1.95 meters. Now that's just saying that I am 1.95 meters away from where I started. Now we could also look at a displacement in between other time segments. So we could also look at a displacement from 2 seconds to 6 seconds. So we could look at a displacement in that case. And so now our delta x is still going to be this x final minus the x initial. But the x final in this case is going to be the 1.95, and the initial will be the time that we're now saying is 0. So going between 2 and 6 seconds, it took 4 seconds to do this, and it started at this 0.65. So the displacement in this time frame would be this 1.95 meters minus 0.65 meters, and that's where we would get our 1.95 minus 0.65, and we get a 1.3. So 1.30 meters. That would be the displacement for this time frame. So there's another way that we can get to seeing that this is a constant velocity. If we see that these are about evenly spaced, then we know that this is going at a constant velocity. If they get closer together or they get farther apart as time moves on, then that means that the car is speeding up or slowing down. So then there's another way to show that this is also moving at a constant velocity. So that's where we can get this position first time graph. And as we graph our data going from this 0 all the way to 20 seconds, we should get a graph that looks pretty linear here. And then we can use this y equals mx plus b. As we use y equals mx plus b, we can derive a new equation. This term derive might seem scary, but it's really not if we use if we use this y equals mx plus b. Instead of that, I like to think of it as the y-axis equals to a slope times x-axis plus the intercept, which I'll just leave it as b. So we are going to have a y-axis. It's equal to a slope times an x-axis, and this y-intercept, that's where we start. That's where we start at time equal to 0. So we're going to take what we have on the y-axis, which is just our position. So on our y-axis, we have position. And then it's going to equal to the slope, and the slope of this is going to be that velocity, v. And on the x-axis, that's this time t. And then we're going to add in this y-intercept, and that is, once again, that initial position. So we can derive this equation, x equals to v times t plus x naught. And then as we get any graph, I'm going to say this throughout the course, that whenever we have any graph, we can either get the slope or the area, and either the slope or the area is going to tell us something. And then we can compare it back to our equation sheet, and then maybe once we compare it back to this equation sheet, then that will tell us some information. So if we get a slope, whatever a slope is, that's going to tell us a change in the y-axis divided by a change in the x-axis. So in this, our change in our y-axis is the change in our position, which is our displacement, and a change in our x-axis is a change in time. So what we're getting here, if we have a slope, is we have a displacement over time. And so what that is that velocity. And that velocity is the slope of this graph. That is your displacement over our time. And then if we were to get an area, well, that's what this graph, on this graph, we first see that we have a constant slope. So whatever velocity we get, it would be a constant velocity. Constant slope would be this constant velocity. Now, if I'm talking about an area, what we do to get an area of a graph is you shade in below the line to the horizontal. So then we're going to take what we have on the y-axis and multiply it by what we have on the x-axis. So to get the area of a graph, we get the y-axis multiplied by the x-axis. So in this case, the area of this graph is going to be position times time. So it would be x times t. Now, what I want to do is I want to take these three different equations that we just assembled and I want to try to make sense of some of them. I want to refer over to our equation sheet because we're going to find out that the area doesn't have to do with anything. But if we look at our equation sheet, these first three equations, this is all the kinematics unit. Everything is in this first three. So this is where we're going to stay, and this is where we're going to look. Now, I see xv times t plus x naught. So if I look on here, I have only one equation where it's x equals. So that's this second one. And if I remove this back term, this 1/2 at squared, this a is for an acceleration. So there's no acceleration. So the equation we derived, this x equals v times t plus x naught, v times t plus x naught is equal to x. So we were able to derive this equation. And if we were to solve for this velocity v, it would be the x minus x naught divided by time, which would be the slope of this graph. So we have the change in the position over the change in time, which would be our displacement over time to be our velocity. And that's how we can get with this equation here. We also derived the first component of it. Now I don't see anything where I have position times time. I don't see any equation where I have x times t. I don't have anything where I see x times t. So sometimes the area actually means nothing. Sometimes the slope means nothing. But in this case, we know something from the slope of the graph and we know something from the slope-intercept formula. Now, from this, I want to take us to some example questions that we can have. So, that's where we're going to get to this question in here, where we have a student is provided with a battery-powered toy car that a manufacturer claims will always operate at a constant speed. So that's the claim that they're making in this problem, is that they will operate at a constant speed. And then what we're saying is that a student must design an experiment in order to test the validity of the claim. And we're trying to find which of the following measuring tools. So we're going to look at some measuring tools, and we want to try to test the validity of the claim. And so we're going to get two answers on this. So in this, it says here that there's these photo gates that can be placed at the beginning, end, and at various locations along the track that the car travels on. And what a photo gate is, a photo gate is a place where light, there's this picket fence where one area is dark and one area is clear. One area is dark, one area is clear, one area is dark. And then it's going to move where there's this sensor and this light beam. This light beam creates this beam of light that goes over to a sensor that it can tell if the light is hitting it or if the light is not hitting it. And then this thing here will move with a velocity v going into the sensor, breaking the light beam. And so then when this part, the dark part, is going through it, the light beam is off for a certain amount of time. And we know the distance of it, so we can get then a distance over a time. And then once this light beam goes through here, then the light beam is on for a certain amount of time. So we know then the displacement over time. And then the light beam is off, where we know then the displacement over that time. Then once again, we'll have the displacement for when the light is on. And then we'll have a certain amount of time with it off, a certain amount of time with it on, a certain amount of time with it off, a certain amount of time with it on. If we know the distance here, then in this case, we would be able to get a velocity. So a velocity being that displacement that's known over that change in time. So we would be able to get a velocity in this. So getting these photo gates to be placed at the beginning and end of the various locations, we would be able to get a velocity. Now, that doesn't mean that the thing is going at a constant speed, but we can measure this and we can test the validity. In other words, we can test to see if it's true or if it's not true with this tool. Another tool is definitely to use this meter stick, because we know a meter stick will tell us a certain position, and by knowing the position and then the meter stick, we can again get time in another way. This is just one of the tools. It doesn't mean that this is the only thing. We used our meter sticks in order to get the distance that the car was able to travel. Now, if we had a motion detector oriented perpendicular to the direction of motion, so that means if the car is moving this way and I am sensing everything that can move in this direction. So if we have a velocity going this way and I can tell if something's moving up or down, that term perpendicular makes it so that way this motion detector would not pick up anything. And mass really would do nothing to tell us about position and velocity and time, because we know that this velocity is this change in position over change in time, or displacement over time, so the mass has no effect. Lastly, on this question 11, or rather this question here, where we have these points that are on this tape. So a student performs this experiment with a toy car. It's on this ticker tape that places dots at tape at equal time intervals. So in other words, just like as we did our car lab, we could say that this is time 1, this would be time 2, and it could be either 2 seconds apart or it could be 1 minute apart, but either way, the time intervals is equal. And then these dots, they represent the motion on this, having the positive direction be along the axis. So we're given a positive going to the right as positive. And so we're asked, which of the following experiments could the students have conducted to create the data shown on the tape? So what I see here is these points are close together, then they get farther apart. So this delta x is small, then the delta x gets big. So if the delta x is small, then it has to be moving slow, and if the delta x is big, then it has to be moving fast. So we see that initially the increases in speed, so we can eliminate option C and option D, because the toy car definitely goes increasing speed, where it says in C and D that it decreases speed. So then as we look, this delta x is big, then it gets to be getting closer together. As it gets closer together, that means it has to decrease its speed, because how far apart it is, that's the displacement, divided by the equal number of time, that means it has to be going slower here. So we have it that it increases its speed, goes at a constant speed, I like that, and then it should decrease our speed. So then this would be our option B, because it goes increase to constant speed to decrease its speed.